Very good morning, students. Today we are going to see the topic of talk about an axis. In last class we have discussed what do you mean by talk. Talk is nothing but the symbol of tau represents as tau equal to the product of position vector and the force, applying force. This is a talk. Okay, torque is nothing but as the moment of the external applied force about a point of axis of rotation is called as torque. In this case, we have deal with last classes of torque about a point axis, point, not an axis. In this session, we deal with the torque about an axis. Let us consider a rigid body. Rigid body is nothing but a rigid body is the one which maintained its definite and fixed shape even when we are applying of external force act on it, which means சிம்பிளாக சொல்லலாம், ஒரு ஃபோர்ஸை அப்ளை பண்ணுற ஒரு ரிஜிட் பாடி மேலே ஃபோர்ஸை அப்ளை பண்ண பிறகு என்ன பண்ணால் the body does not changes its definite shape and signs is called as rigid body. So here we are taking as a rigid body rotating about an axis. Here AB be the axis. Let the force F act on a point at point P. The force F may not be in the plane of A, B, P. So we can take the origin O at random at any point of the axis. Any point of the axis. So here it is taken as the origin O. Then the torque of the force F about the origin O is tau. We know the formula tau equal to R cross F. The component of the torque along the axis is the torque of about its axis. To find, we should first the vector tau vector equal to R vector cross F vector and the angle of phi between tau and AB. Here F is not in the plane of ABP. Then the torque about AB is parallel component of R cross F, magnitude of R cross F cos phi, and the perpendicular component is R cross F and sin phi. Then further we can move. The torque about the axis will rotate about it, which means the torque about it, the axis will rotate the object about its axis, and the torque is perpendicular to the axis will turn the axis of rotation when the body exists simultaneously on the body which have precision means is nothing but rotation. One can witness the precessional motion in the spinning top. Here the rotations, which means a body will be rotated about its axis and precision will be occur the rotation of the body. This is talk about an axis. Next, an important 5 more questions. What are the relation between torque and angular acceleration? Let us consider a rigid body rotating about its axis. A point mass m in the body will be execute in the circular motion, fix its axis. The force F acting on the point of the mass is tangential force. So this force is perpendicular to the position vector R. The force is perpendicular to the position vector R. The position vector of the point mass is tells us R vector. In the torque produced by the force on the point mass about, we can write as tau equal to R vector cross F vector. Here we are write as the cross product, so we can find the magnitude of the cross product. So tau we can write as tau equal to RF and sin theta. Here the theta becomes 90 between R and F. So sin theta becomes 90, sin 90 becomes 1. So substitute the value of sin 90 in this equation. So we get the equations tau becomes RF. According to Newton's second law, F equal to ma. So substitute the value of F into this one. So tau equal to R, then after F replaces ma. Then after we can move furtherly, Rm to write is Rm, and a relation between linear acceleration and angular acceleration, a equal to r alpha. So substitute the value of a becomes r alpha. So we can write these equations tau equal to r into r m into alpha. So r into r becomes r square. So we can write as this equation to change as modified for us our conveniently. Tau equal to m r square alpha. Hence the torque force acting on the point masses produces an angular acceleration alpha in the point mass about the axis of rotation. We can write as in vector notations. Tau vector equal to the product of mass into square of the distance. This means position vector in alpha. And here it is. Let's see the diagram. The directions of tau and alpha along the axis of rotations. Along the axis of rotations. If the directions of tau is the directions of alpha, so tau and alpha becomes same directions. In other hand, tau is opposite to the alpha, angular acceleration or retardation. Further, the term m r squared, this is the term m r squared in equations 5.14 and 5.15, we can write as or called as moment of inertia. So substitute the value of inertia in these equations of 5.14 and 5.15. Here a rigid body is made up of many such point masses. Hence the moment of inertia of a rigid body is sum of the moments of the inertia, all such the individual point masses. So we can write as the moment of inertia of the body I equal to summation of individual masses, sum of the individual masses in sum of the square of the position vector. We can write as, so tau becomes summation of mi ri squared into alpha. So we know that mi ri squared we can write as moment of inertia. So tau becomes I alpha. This is the relation between torque and angular acceleration. The same method we can move another topic of angular momentum. So angular momentum. Angular momentum in rotational motion is equivalent to the linear momentum in translation. Translation is nothing but direct motions or linear motions or straight line motions. The angular momentum of a point mass is defined as the moment of its linear momentum. In other words, the angular momentum L of the point mass having a linear momentum P at a position vector or with respect to the point or axis. So we can write as mathematically angular momentum L vector equal to R vector cross P vector. So we can write as the magnitude of the angular momentum, we can write as L equal to Rp sin theta. We know that cross product can be neglected by using of the magnitude of sin theta. Here theta is the angle between the position vector and the linear momentum P. L is the perpendicular to the plane containing R vector and the linear momentum P. So as we have written as the case of torque, here also we can associate the angle sin theta, either R or P. Then L equal to R into P sin theta simplifies. The angular momentum L represents r into p sin theta, which is equivalent to r into p perpendicular. In another form, angular momentum L equal to r sin theta into p equal to r perpendicular into p. Here, whereas p perpendicular is the component of the linear momentum p, which is perpendicular to r. Similarly, r perpendicular is the component of position vector r, which is perpendicular to p. The same cases of angular momentum like as linear momentum. The angular momentum is 0, L becomes 0, and also the linear momentum becomes 0, P becomes 0. Or if the particle is the origin, the position vector R becomes 0, or R vector and P vector are parallel or anti-parallel. Parallel means like as angle theta equal to 0 degree, anti-parallel means theta equal to 180 degree. And finally, there is a misconception that the angular momentum is a quantity that is associated only with rotational motions. It is not true. The angular momentum is also associated with the bodies in the linear motion. Another important 5 mark, the same way we can measure angular momentum in angular velocity. The same process. Let us consider a rigid body rotating about in axis m with the point mass. The m with the point mass will be executing a circular motions about its fixed axis. Then the point mass m is a distance or from the rotational axis. It is in a linear momentum at any instant. P is acting a tangential from the circular motions. L is perpendicular to R and P. The angular momentum L is perpendicular to R and P. Hence, it's directed along the axis of rotations. The angle theta between R and F in this case of 90 degree. The same way, the magnitude of the angular momentum L can be written as, we know that angular momentum write as L equal to R vector cross P vector. So write in magnitude, or P represent as mv. We cancel the cross product, so applying a sin theta. This is a magnitude of angular momentum. So we can write as L equal to R mv sin theta. Here theta becomes 90, so we can put the value of sin 90 becomes 1. So further we simplify these equations. L becomes R mv. Here V be the linear velocity, and also we know that in second lesson the relation between linear velocity and angular velocity becomes V equal to R omega. Hence we substitute the value of V in this equation, so we put it right as L becomes R m, V replaces R omega. So write this method. So L equal to R m R omega. Here R into R becomes m r squared. Already we have discussed m r squared is nothing but the product of square of the distance or position vector is called as moment of inertia. So the directions of angular momentum, which is axis of rotations, the above expression can be written as L vector equal to m r squared omega. The term m r squared already tells us moment of inertia. A rigid body is made up of many such point masses. Hence the moment of inertia of a rigid body, the sum of the moments of inertia for all the individual point masses. So we can write as here following methods: I equal to summation of mi r squared. So put the summation value, angular momentum L vector equal to m r squared becomes right as summation of mi r I squared into angular velocity omega. So replaces this bracket terms will be right as I. So L equal to I omega. This is the relation between angular momentum L and angular velocity omega. And further, the important one more topic, torque and angular momentum. The expression for the magnitude of the angular momentum of a rigid body is L equal to I omega. This is the magnitude of the angular momentum. The same way, the magnitude of the torque of a rigid body, tau equal to I alpha. So further write the expression for tau equal to I alpha. We know that tau equal to I alpha. Alpha represent as d omega by dt. So tau we can write as I into d omega by dt. Omega is the angular velocity and alpha is the angular acceleration. So we can modify these equations like the method of tau equal to d by dt of I omega. We know that L equal to I omega. So substitute the value of I omega becomes angular momentum L. So tau becomes dl by dt. The above expression says that external torque on a rigid body is fixed and axis produces the rate of change of angular momentum in the body about in the axis. The same process we can write as the force. F becomes, according to Newton's second law, F becomes dp by dt. This is an torque, this is an force. This is an rotational motions, this one is an linear motions. Next topic, conservation of angular momentum. From the above expression we could conclude that the absence of external torque, the angular momentum of a rigid body or system of particles is always conserved. So tau becomes 0 here. Tau becomes 0 and also dl by dt becomes 0. So L becomes constant. This is a conservation of angular momentum. And next topic, equilibrium of rigid bodies. Equilibrium of rigid bodies is nothing but, suppose when a body is at rest without any motions on the table. I once again repeat, when a body is at rest without any motion on the table, we say that there is no force acting on the body. Actually it is wrong, because there is a gravitational force acting on the body in downward direction and also the normal force exerted by the table on the body upward direction. So these two forces cancel to each and there is no net force acting on the body. There is a lot of difference between the terms no force and no net force acting on your body. The same arguments holds good for rotational conditions in terms of torque and moment of force. So here a rigid body is said to be a mechanical equilibrium when both its linear momentum and angular momentum remains as constant. When the linear momentum remains constant, the net force acting on the body becomes 0. So F net becomes 0. I repeat, the linear momentum remains constant, the net force becomes 0. In these conditions, the body is said to be in the translation equilibrium. Translation means linear. This implies that the vector sum of the different forces F1, F2, F3 acting in a different directions of the body is 0. So we can write as F1 vector plus F2 vector plus etc. plus Fn vector becomes 0. If the forces F1, F2, F3 act in the different directions and the body, we can resolve them into horizontal and vertical components and take the resultant in respective directions. In this case, there will be horizontal as well as vertical equilibria is possible. So we conclude that similarly, when the angular momentum remains constant, the net torque acting on the body becomes 0. So the net torque becomes 0. Under these conditions, the body is said to be a rotational equilibrium. The vector sum of the different torques tau 1, tau 2, tau 3 producing different senses of rotations of the body becomes 0. So we can write as the same method tau, the adding sum of the torques becomes 0. Thus we can conclude a rigid body in mechanical equilibrium when the net force and net torque acting on your body becomes 0. This is the conditions of equilibrium of rigid bodies. The table provided here, table 5.2, table 5.2 tells us different types of equilibrium and their conditions. Here there are types of equilibrium: translation, rotational, static, dynamic, stable, unstable equilibrium, and finally neutral equilibrium and the conditions. So just read out the tabular column to analyzing what are the difference between one to each others. Okay, good. So next we are going to see the another topic, couple. Let's see the diagram. AB is the thin uniform rod, C be the center of mass. Let two forces acting, which means equal magnitude and opposite direction. Whereas the rod AB is perpendicular to it. There are two forces are separated at a distance of 2r. As the two equal forces are in opposite directions, they cancel to each other. A act as downward and B act as upward. So the magnitude becomes same, but the directions will be opposite. So they cancel to each other. The net force acting on the rod becomes 0. Now the rod is in translation equilibrium, but the rod is not in rotational. I repeat, now the rod is in translation equilibrium, but the rod is not in rotational equilibrium. Let us see how it's not in rotational equilibrium. The moment of force applied on at the end of A taken as with respect the center of mass C produces anti-clockwise direction. Similarly, the moment of force applied the other end B also produces of anti-clockwise rotations. So the moments of both forces, the case of same sense of rotations the rod. So thus the rod undergoes through a rotational motions during or turning, even though the rod is translation in equilibrium. So what do you mean by couple? So couple is nothing but a pair of forces which are equal in magnitude and opposite direction and separated by a perpendicular distance, so that their lines of action do not coincide with the causes of tuning of effect is called as couple. Next we are going to see the topic of principle of moments. Consider a light rod. Consider a light rod, they having negligible mass which pivoted at the point along its length. The two parallel forces F1 and F2, the ends of the distance between F1 and F2 is D1, D2 respectively to the pivot to the normal reaction force N at the point. Here, if the rod has to remain stationary in horizontal position, it should be in the translation or rotational equilibrium, then both the net force or net torque must 0. So we can write as minus of F1 because of the force acting in downward direction, so we put negative sign, and also F2 acting in downward direction, so we put minus F2. So minus F1 plus N and minus F2 becomes 0. So simplify these equations, we get N equal to F1 plus F2. The net torque D1 F1 minus D2 F2 becomes 0. So equate these equations. Then after we get the equations of 5.33 becomes D1 F1 equal to D2 F2. So we find the value of F1 and F2 becomes D2 by D1. Here F1 is the load and F2 is our effort. In this stage we get the advantages. D1 is less than D2. F1 is load, F2 is effort. D1 less than D2. So the distance is very large, D2, when compared to d1. In this case, the ratio of d2 by d1, the ratio of d2 by d1 is called as mechanical advantages of the simple lever, which means the pivoted is called as fulcrum, which implies we could if the large load with small effort. This is mechanical advantages we can write as d2 by d1. There are so many simple machines that work on the above mentioned principle, but a large amount of work carried by small amount of effort. Finally, we are going to the topic of center of gravity and conclude this and quite the links also. Let us consider a rigid body made up of several point masses. Such the point masses experiences gravitational force towards the center of the earth, because the size of the earth is very large when compared to the point masses of a rigid body. These forces appear acting parallelly downward. The resultant of the parallel forces always act in the point of. The point is called as center of gravity of the body. The center of gravity of the body is the point at which the entire weight of the body acts irrespective of the position and orientation of the body is called as center of gravity. So the center of gravity and the center of mass of a rigid body coincide when the gravitation field uniform across the body. The concept becomes we have maintained in the lessons of 6th lesson. Further we can move. We can also determine the center of gravity in uniform lamina of even irregular shape of pivoting it at various points of trial and error method. The lamina remains on horizontal at the pivot point where the net gravitational force acts as the center of gravity. When the body is supported at the center of gravity, the sum of the torques acting on the forces of a rigid body becomes 0. Moreover, when weight is compensated by the normal reaction force exerted by the pivot, this body is static equilibrium, hence it remains as horizontal. So another example of, there are also another way to determine the center of gravity of irregular lamina. We suspend the lamina for different points like as P, Q, or then after vertical lines of P, P dash and Q, Q dash and or dash through the center of the gravity. Here the reaction force acting on the point of suspension and the gravitational force acting on the center of gravity cancel to each other, and torque causes by the also cancel to each other. This is under determinations of center of gravity plane lamina by pivoting, and this is the determinations of center of gravity by lamina by suspending. Okay, good. This is our last topic of center of gravity. Okay, good students. So providing some assignments, read and follow the link. If you have any doubt, kindly ask me. Thank you so much.